All right, good afternoon. This is Mr. McMurray, and we are here for Chapter 3, Newton's second law of motion, dealing mostly with force and acceleration. Okay, a couple things. First of all, let's talk about Galileo again. Galileo, remember, was running his balls down the ramp, okay, and he was timing them, usually with his heartbeat or something like that, not real sophisticated equipment. But he noticed that things we said that went downhill sped up, okay, and things that went uphill slowed down, okay. And not only that, but he noticed they did it the same way every time. If he took a ball and dropped it up here, it would basically speed up at the same rate every time. It would pass each point along the way at a certain number of seconds. Say this was 1 second or maybe two heartbeats, whatever. And there's 1, 2, 3, and 4, and 5. And every time he did it, they would speed up at exactly the same amount. Okay. And this is the idea of acceleration. Okay. Acceleration is how much change in the speed or velocity is there over time. In other words, are you speeding up or are you slowing down? Okay. So the definition for acceleration is change in velocity over time. Okay, so we know that can be speeding up and slowing down, but velocity also includes direction. Otherwise, we could just put speed up here. Okay, but velocity also includes direction. So one, that means that acceleration is also a vector quantity because it has velocity in it, which has a direction. It also means that you could change your acceleration by changing your direction. So normally we think of acceleration as speeding up, but it can be speeding up, slowing down, or changing direction. Okay, the units are meters per second squared. I'm going to go over all that again, but meters distance is meters per second, or it could be miles per hour or whatever, and then divided by the time it takes for it to change those number of miles per hour. So it's the change in the velocity in a given amount of time. And so if I went from 0 to 60 in 3 seconds, it would be 60 miles per hour per 3 seconds, which if I divide that out, would be 20 miles per hour per second. And that's how much I'm speeding up. Keep in mind that acceleration, if it's 0, just means that you are not speeding up and you are not slowing down. Okay? It does not mean that you are not moving. Okay? Just acceleration can be 0. Now, if your velocity is 0, yes, then you're not moving. But acceleration just means that you are not increasing or decreasing. Also, let's say that I say, oh, my acceleration decreased. Does that mean I'm going slower? No, that means I'm not going faster at quite as much a rate. Okay, let's say I went from 0 to 60 in 3 seconds, and then I went to 70 miles per hour in 2 more seconds. Well, I went from 20 miles per hour per second to 2 miles per hour per second. If I did that right, or 5 miles per hour per second. Sorry, 5 miles per hour per second. All right. In other words, I'm still speeding up at 5 miles per hour per second, but I'm not speeding up nearly as much as I was before. So my acceleration has decreased. Okay. And so basically, that's some things we need to talk about. Now, like I said, acceleration, we think of speeding up. Deceleration or negative acceleration is just slowing down. All right. And then you could also now, Galileo couldn't explain things. Once again, that's why his name's not in the law. Newton explained it a little better. But one, he could explain that gravity was the force that was causing these things to accelerate as they went downhill. And so the most common acceleration that we have and we talk about is usually that of gravity. Okay, and so gravity is accelerates things, it turns out, at a speed of 9.8 meters per second squared. Now, to make it easier, we're just going to round that off to say 10. Okay, so at 10 meters per second squared. Okay, it's practically the same thing. All right, and it makes the math a lot easier. So if we're going at if we're falling, someone falls off a building, that means after 1 second, it will be going 10 meters per second. After 2 seconds, it'll be going 20 meters per second. After 3 seconds, it will be going 30 meters per second, and so on and so on. And that's why the distances, for example, on these balls that are being pulled downhill by gravity keep increasing. Why? Because your speed or velocity is increasing every second by 10 meters per second. Now, there are some limits on that. We'll talk about that later, but for right now, that's basically when anything is dropped, doesn't matter what it is, it accelerates at that rate. Okay, and that's what was making it slow down. Now, one thing we need to look at this. All right, maybe it's not coming up. There we go. Okay, let me move my face out of the way here so you can see this. But okay, it says what will be the acceleration of a rock going straight upward at the moment it reaches the tippity top of its trajectory? In other words, right here at the very top. Well, we know the speed of the ball at that point would be 0. It was going up, it stops, and then it comes back down. Someone said, well, what's the acceleration right then? Give me a second to think about it. Everybody got your answers? All right. It is exactly the same as it was right before that and the same as it was after that, which is the acceleration of gravity. Now, when it's trying to go up, we would say it's a negative 9.8 or 10 meters per second squared because it's slowing down. When it comes down, it's speeding up, so we call it a positive. It's a positive acceleration of 9.8 meters per second squared. Okay, so its acceleration right there at the top is 9.8 meters per second squared, just like it, or 10 meters per second squared, just like it was right before and right after. Because even though it's technically stopped right there, right before there, it was moving up at a slower speed, and right after that, it is going down. So it's constantly changing its velocity. We could pick a point right here and say, oh, at that point, it's going 3 meters per second. Okay. But right before that, it was going faster or slower. So if there's no change in velocity, there's no acceleration. And in this case, it is changing its velocity. Therefore, it is accelerating at the same rate there as it is all along the way. Why? Because gravity is accelerating it, decelerating on the way up, accelerating it on the way back down. It is still accelerating or changing its velocity. All right, because right before that, millisecond before that, millisecond after that, it has a different velocity. So it is constantly changing, and it has the same acceleration it does anywhere along the way there, 10 meters per second squared. All right. Let's see here. So we talked about inertia last time. Inertia says the more mass something has, the harder it is to change its direction. Okay, and keep in mind, mass is not the amount of space it takes up. That's volume. Okay, mass is how much stuff there is. Okay, how much matter makes something up. For example, I have this little clamp right here. Okay, so mass is just how much atoms make this up. Okay. It is also not the same as weight. Weight is the force of gravity pushing me down. Okay, so just for a second, let me get my scales over here. We use scales to measure weight. Why? Because, I don't know if I can get this where you can see it. Anyhow. All right, here's see it. I put the scale down here. When I step on the scales, gravity is pulling me down. That's what the scale measures. And so it says, oh, you weigh 209 pounds. I may not like that, but that's what it is. That's the way it is, okay? And that's because gravity is pulling me down. If I went to the moon, then I would have a different weight. Why? Because there's only 1/6 as much gravity. So you could divide that by, take 1/6 of that, divide by 6. 30-something pounds. All right, hey, I could lose weight. Okay, so the easiest way to lose weight is go to the moon. Unfortunately, unless you're a multimillionaire or something like that, it's a very expensive way to do it. Okay, so not really practical for most of us. Okay, mass on the other hand doesn't change. If I have the amount of stuff in my body here or I'm on the moon, doesn't matter. Same amount of stuff, right? Okay, so mass is how much there is of it. All right, and the mass is going to affect how fast things accelerate. And that's something that Galileo and Newton noticed, that if something has more mass, then that affects how quickly it will accelerate. Pretty obvious example. Let me just get my little bowling ball out. All right. If I have my bowling ball, let me pause for a second and get set up. All right, here we are. So basically, there's two things that affect how fast something accelerates, okay? One has to do with mass. Say I have this little plastic golf ball, it's not even a real golf ball, okay? And I have this bowling ball, all right? If I apply the same amount of force to the bowling ball, it will speed up at a certain rate. It will accelerate, okay? If I put the same amount of force on the golf ball, it will accelerate faster. Why? Because we're putting the same amount of force on two different masses, okay? If I put it on a big mass like the bowling ball, it's not going to accelerate as fast. If I do it on the small one like the golf ball, which is over across the room, then it's going to accelerate a lot faster, okay? And so basically he said the acceleration is proportional, directly proportional. In other words, if one increases, the other increases. If I put more force, it's going to accelerate faster, okay? If I put more. I got my things mixed up here, but that's okay. We'll go ahead and do this. It's proportional to force. The more force, if I have this bowling ball, if I just barely put a little force on it, it's going to accelerate, start moving, but it's not going to move very much. Okay. If I put more force on it, then it's going to accelerate faster. And if I were slinging it down the bowling alley, then it would put even more force behind it and it would accelerate even faster. Okay. Now, when I say the force, notice once I let go of the ball, am I putting any force on it? No. Okay. So it's going to accelerate when I put the force on it. Once I let go of it, is it accelerating? No. Okay. It's going to have friction and things starting to slow down, if anything, so it may decelerate some. But it's going to accelerate only when I'm applying the force. Okay. So force is directly proportional, but like we showed with the golf ball, it's inversely proportional to the mass. The bigger the mass, like the bowling ball, okay, versus, got lots of balls here. Well, let's say a ping pong ball, same thing that we did with the golf ball. Okay, the smaller the mass, the bigger the acceleration. Okay, because it has less inertia, therefore it's a lot easier to make it accelerate. You don't have to overcome as much inertia. If I accelerate the ping pong ball, it's going to accelerate pretty fast. The bowling ball is not. Now, so if we put those two things together, force is directly proportional, mass is inversely, we come up with a formula. And that says that acceleration is equal to the force divided by the mass. Let me see if I can get out of here. And we'll look at this. Okay. And that was one thing that Newton did, and why he gets credit for the laws, because he put it mathematical. I mean, this was a guy, after all, who in his spare time invented calculus, okay? All right, so we can say that acceleration is equal to the force divided by mass. The bigger the force, the bigger the acceleration. The bigger the mass, on the other hand, the bottom of the fraction, it's going to make the acceleration less if you apply the same amount of force, okay? And that is basically what Newton's second law says, because acceleration is inversely, or 1 over the mass, and it's directly proportional to force, you end up with acceleration equals to the net force divided by the mass. Okay, that makes pretty good sense. Okay, now let me do another experiment and we will talk about it a little bit more. All right, the first experiment, you're going to take my word for it a little bit. I don't know if you can see it here or my camera. It looks pretty blurry from my end. But when in here we have 3 sets of balls. We have the white styrofoam, we have some glass marbles, and we have some steel ball bearings. Okay. When you take things around, when they hit each other, they apply force on each other. Actually, equal and opposite, but we'll get to that next week. But the ones that move the fastest when you move them around when they get hit are going to be the white styrofoam. Why? Because they don't have much mass. So when they get a force action on, boom, they move and accelerate very quickly. Okay. The glass marbles weigh a little bit more. So when they get hit, they don't accelerate as fast. Why? Because they have more mass. And finally, the steel ball bearings have the most mass, and so when they go where they want to. They don't get changed much by the other two because the force is not enough to make their mass accelerate very much because they're quite a bit heavier. Okay, so that's kind of an example of just showing how the force and mass, these are all the same forces, but the different masses causes them to accelerate differently. All right, let's try one more thing and we'll see if we're ready to really understand it. This is the advanced course one. All right. All right. Now, this is one of my favorite experiments, partly because it took me years to find this. This is the dart gun with a stiff dart. You can't find those anymore. They're always got some flexible darts, and they're not worth diddly, especially for this experiment. Now, glued or taped to the dart, I have put a golf ball on this side and a ping pong ball on this side. Okay, so before we do that, let's wait for a second. All right, let's say I drop these. Never mind. Let's do it gently first. Okay. Let's shoot them. Okay, we're going to shoot them. These are identical guns, so they should apply identical forces. Okay, so we're going to see what happens to them. I'll scoot back a little farther. Oops, let me tilt this down a little bit so you can see more. All right, there we go. Maybe that'll do it. Okay, and so I'm going to do it 1, 2, 3, and you will notice that, or should have noticed anyhow, that the styrofoam ball went a lot faster. Okay, now if we're applying equal force, and we know this one with the golf ball has a lot more mass, same force, bigger mass. We know it's going to accelerate slower, and that would explain then why this one went slower and this one went faster. Okay, now that's pretty straightforward. So, well, that makes sense. All right, let's try something different now. All right, let's just drop these at the same time. And which one's going to hit first? Well, we should know the answer, but let's just see if we do or not. Hang on. Sophisticated camera work here. Gotta work it. Okay. So if I drop them at the same time, I don't know if you can still see when they hit the ground. Let's try that again. Okay, if I drop them, they hit basically at the same time. Okay, pretty close. All right, much closer than on the other one. Now the other one, ideally, we should post it in slow-mo, and I may do that so you can see it. But this time they hit at the same time. Okay, someone says, well, what force is making them fall? Well, gravity. All right, now the mistake people make is they think, oh, it's the same force, so it's equal force. And that is incorrect. Any two items will fall at the same time, but it's not because the same amount of force is acting on them. In fact, just the opposite. All right, the mass of an object determines the amount of gravity that will act on it. Okay. The bigger the mass, the more gravity acts on it. So there's actually a bigger force acting on the golf ball and a smaller force acting on the ping pong ball. Hopefully I keep putting these on the same side. I forget. But yeah, so it's not the same force. This has a bigger force because it's a heavy golf ball. This has a small force because it's a small mass ping pong ball. Okay, and so the force is not the same. All right. Now, because the mass is different, though, this has a bigger force because force of gravity acting on it, but it also has a bigger mass, which means it has more inertia to overcome, to get going. So it turns out that a big force acting on a big inertia or a big mass falls at the same rate as a small force acting on a small mass. Okay? So the reason gravity makes all things fall at the same rate or accelerate at the same rate is not because the force is the same. It's because the force is more on a heavier object with more mass, but so is the inertia or the resistance to acceleration. And so it works out the same. Now, if you look at the formula, acceleration equals force over mass, that makes sense. A big force divided by a big mass is equal to a little force divided by a little mass. Let's just say this was 20 times more. Well, 20 times more force divided by 20 times more mass gets you 1. Say this one is 1 divided by 1. Well, guess what? That also gets you 1. So they would have the same acceleration of 1 meter per second. Now, technically, it's more like 200 to 1, and that's why you divide it and you get 10. And the acceleration of gravity, we say, is 10 meters per second squared. All right? But they fall at the same rate, not because the force is the same, but because the force is greater, but so is the mass, and that makes the acceleration formula comes out the same. Okay, so that's very important things right there. All right, let's stop for a second and come up with another. All right, use my handy dandy scale here. I weigh, if I step on this, about 209 pounds. But this says also that I can change it, push a little button in the back, and it will say that I weigh 93.7 kilograms. Whoa, I thought grams measured mass, and yet I'm using a scale that measures weight. How can I do that? Well, here's the deal. On Earth, the pull of gravity is the same everywhere. So if you know how much mass you have, then when you step on the scale, if you know that's how much you weigh, then we can adjust based on Earth's gravity, we can adjust for that and solve for how much you would weigh. And that's really all the scale is doing. It's doing that. Now, technically, the farther you are from the center of the Earth, you have a little bit less gravity. But if you get on the highest point, Mount Everest, I think we calculated it, and it's almost like 1/10 of a pound, okay? So it's not like you can go climb a mountain in Colorado and all of a sudden, woo, I lost weight, okay? It's not enough that you would notice, okay? Because we're talking compared to the distance of you to the center of the Earth to you from the center of the Earth on top of a mountain, it's a minuscule amount of difference. And so basically we can adjust. If some two objects on Earth have, I would say one has twice as much mass, then we can say it's also going to have twice as much weight, okay, because the amount of gravity is consistent on them. And so we can adjust that, okay? They're proportional. They're not the same thing. Weight is just gravity pulling on you, and mass is how much there is of you. But on Earth, if the gravity is the same wherever you're at, but let's say on Earth, then they're proportional to each other. And if you double the mass, you're going to double the weight, okay? As long as the amount of gravity doesn't change, which is true most of the time here on Earth. All right, let's talk about friction for a little bit. Let me get an experiment kind of set up, and let's talk about that. All right. Part of the genius of Galileo, and then later, of course, Isaac Newton, is that they recognized friction was a force. We can't see friction most of the time. Sometimes if we rub our hands together real fast, we can feel the heat from it. That's how we keep warm. So if you're out cold, you rub your hands together. Okay, so all of those things can affect how friction. So let's think about some of the things that affect friction. All right. If I put this board, I have a little block here, and I have sandpaper on one side, plain. If I put it on the plain side and I pull it, and I measure the amount of friction, which is about 120. If I flip it over on the cardboard the sandpaper side, well, I expect more or less friction. Well, quite a bit more. Okay, why? Because we have a rough surface. Okay, so obviously something about the surface has to do with it. Now, if we put it on the table, which has a smooth surface, with the smooth of the board, we would expect more or less. Well, less, and it turns out we get about, looks like around 75 or so. So it's less than it was on here. Here it was closer to 90. All right. Now, if I flip it over to the sandpaper side, will we get more or less friction than when we had the flat board side? Well, let's try it. Actually, it turns out we have 50%. Whoa. Someone says, well, that's kind of tricky. Shouldn't the sandpaper have more, just like it did on this one? Well, keep in mind, this is rough, but that means that there's little bumps on it, and only the little tips of the bumps are touching. And on a smooth surface, that actually means you have less surface area touching than you do if I flip over the board. And so since there's less surface to rub, then you have less. Now on this one, you have rough bumps, and they're getting hooked up on each other, and that creates more friction. So it just depends. That's kind of a tricky question because people think, oh, it's got sandpaper, it'll be rougher. But actually, it can be less because you have less surface area actually touching the thing. All right? So all those things are true. Now, what if I put something heavier on this? Got this water bottle. All right, I add more mass, so what's that going to do? And that's going to give us the most so far, 350 things. So Newton, so it's going to give us the highest reading yet. Okay, why? Because obviously if you have more mass, then it's going to press it down into the surface more, therefore creating more friction. Okay, if we wanted maximum friction, we could set this on here, and we could set that on top of it there, and then we could pull on it, and it almost goes off the scale. In fact, it moves the board before it'll actually move the little cart on the board. Okay, so those are some things that affect friction. Okay, when we're talking about surfaces rubbing against each other. All right, we can have how smooth or rough the surface is, how hard they press together. Try this. If you press your hands together and rub them, they get a lot hotter. Okay, so keep that in mind on a cold day. Don't just barely rub your hands together. Push them together, and you'll get a lot more friction, and it will warm up your hands better. Okay, so the amount of mass or force pressing them together, the type of surface, whether it's smooth or rough, and things like that, the mass of the object, and so forth. Okay, so those are all some things that can kind of affect friction. Friction, just for the record, always pushes in the opposite direction. If I'm trying to pull it this direction, it's pushing it in the opposite direction. Okay, it's always going to be in the opposite direction of the object trying to move. So if I'm trying to move this way, friction is always pushing in the opposite direction. All right. Now, one other thing about friction is that when I first start to move this, if I read it, it will go down almost to 100, and then once I start moving it, it goes back to about 75. All right, and so here's something interesting. Because of inertia, we have to overcome the inertia of the object. We actually have to supply more force to get it going. Now, to keep it going at a constant velocity, so no acceleration, the force I pull with has to be equal to what? The force of friction. As long as they're equal, there's a net force of 0, it will move at a constant velocity like we learned last week. Okay, but when I first move it, it's going to take a little more force to get it going, and then less force to keep it going at the same speed. at a constant velocity. I just have to overcome friction. All right. All right, and I think we talked about that in the other lecture, so I'm not going to spend a lot of time on that. Now, the other thing is, these are things about surfaces rubbing together. There's also friction between gases, the air resistance. We're going to talk about that mostly for the rest of the class. Okay, and there can be fluid resistance. If you're swimming, then swimmers try to make their bodies as streamlined as possible. They shave off their hair and ready to go. But they shave off their hair, so there's least air or water resistance, fluid resistance. Technically, we don't hear that much too much. Normally, we hear about air resistance or air drag, okay? Particularly we're talking about cars and stuff like that. So let's set up for some more experiments and we'll do. All right, before we go on, we want to talk about the newtons and kilograms and pounds and how all that relates to each other, okay? 1 kilogram is equal to 10, technically 9.8 newtons, okay? And so 1 kilogram equals 9.8 newtons, all right? Now, that's basically 10. So let's just say it's 10. If I weigh 93.7, then basically I multiply it by 10 and I get 937 newtons. Okay? And so that's not way, if you want to impress people who weigh, ooh, look at my weight, it's 930. Someone asks how much you weigh, you can say, I weigh 937. Not that you necessarily would want to, but that's what it is. Why? In newtons, okay? And in the metric system, if you were going to do your weight, it would be in newtons, okay? And so 1 kilogram is equal to 10 newtons, and that's equal to about 2.5 pounds. And so if I'm 93.7, about 94, if I double that, I get close to 200 something. And so that's why my weight is around 200 pounds, even though it's only closer to 100 kilograms. All right. And so anyhow, that's just kind of the relationship between those. If you want to, people tell them your mass, that sounds much better, 93.7, whereas your weight in newtons, 937, that may throw them for a loop, okay? But that's kind of how they are connected. So we're just going to say that 1 kilogram weighs 10 newtons, and that's equal to about 2.2 pounds. All right? All right. Also, one other thing about that, basically your weight, the formula for weight, basically weight is a force, the force of gravity pushing on something. So we know that force is equal to mass times acceleration. Okay, well in weight it's mass times the acceleration due to gravity, which is little g, and it's equal to 10 meters per second squared. Okay, so your weight, the force, is equal to your mass, in my case 93.7, times g. G is not gravity, g is how fast you accelerate because of gravity. If it was the force of gravity, it would be measured in newtons, okay? And that's what your weight is. Your weight is the force, okay? And so you would do 93.7 times 10, basically, and you get a weight of 937 newtons. And so the weight would be in newtons because that is a force of gravity on my body. Now the force of gravity in your body would be different because you weigh a different number of kilograms, et cetera, and so forth, okay? And everybody's has a different force of gravity or weight acting on them. All right? Okay. On to air resistance. Let me explain some of the instruments we're going to have here. We have a tube here. Now, I don't know how well we'll be able to see this on there. You should be able to see there's a feather floating down. There's also a coin in here. The coin goes real fast. The feather takes a little while to catch up with it. Okay? Now, this is just a regular tube sealed off with rubber stoppers, and it has a little valve on here. All right? Now, we're going to hook that valve up to this tubing and to this machine here. This is a vacuum pump. It sucks out as much of the air as it can in here. Now, it cannot probably make it a complete vacuum, but it's a partial vacuum and almost a complete vacuum. All right? So let me get that set up, and then we'll go on. Okay, this is the exhaust pump. Vacuum pump sucking the air out. It's noisy. We'll come back to that when it's finished. All right. After noise and smelliness later, if we take this and we flip it, and the feather doesn't stick to the side, then they get almost the same time. Now they're not, still can't. I'm not getting good suction. Sorry, that's how it is. You tie a tape line, there you go. But if I take this off, open it, you can see that my finger is stuck on there. Okay, why? Because there's a vacuum inside there. The air pressure is trying to push in to equalize it, and I'm not sure why it's not working for our thing here. I did drop it earlier today, and that might be it. I shut the thing again, but I can get them closer at the same time, but couldn't get them quite there. All right, if I open it though, you can see all the feather blew down this end as it let more air in there. Okay, now if I were able to get a complete suction, then we would have seen that it did indeed, in fact, hit at the same time. We can get pretty close usually, but they have done the same thing on the moon when they last went to the moon. They dropped a hammer and a falcon feather at the same time, and they hit it exactly the same time because there's no atmosphere. Therefore, there's no air resistance. Okay, so when something has nothing but gravity acting on it, no air resistance, whatever, we call that free fall. Okay, and that means the only thing that's acting on it is gravity, and it would speed up at 10 meters per second. It would keep doing that. 20, 10, after 1 second, 10 meters per second, 20 meters per second, 30 meters per second, 40, 50, 60, 70, 80, and it would just keep doing that as long as it fall, and it would get faster and faster and faster and faster. However, until it hit the ground. However, on Earth, that doesn't usually happen. We have an atmosphere, so we have air resistance. And so we're going to look at think about a couple things with air resistance real quick. Basically, as you're going through air resistance, one of the differences between it and other types of friction is that it also depends on the speed of the object. Okay, just a second. Two main things that affect air resistance then are going to be the surface area, which we talked about before. The other two things, rubbing, the more surface area it came in contact with, then the more resistance there would be. But in this case, it's the frontal edge. Okay, so for example, if I could drop a piece of paper like this, straight up and down, and one horizontal like this, they are not going to fall at the same rate. I can catch this one, the other one had already hit the ground. Why? Because it has very low frontal area, leading surface going down. This one, on the other hand, had a big surface area. Okay, same thing if I crumble one of these pieces up. All right, same thing. The one that's the ball is going to fall up quicker. Why? Because there's not much surface area. So surface area is one thing, but the other thing is the speed of the objects. So the faster they're falling, they get more and more air resistance. Think of this: if you're in the car, you stick your hand out the window. If you're going around town 25 miles an hour, yeah, do all the neat little things. Yeah, do a little surfing your hand out the window. Okay, obviously, if you put it pointy like this, the air goes around it. It doesn't affect it too much. But if you tilt it like this, then it pulls it back. Now, say you're on the highway going 60 miles an hour and you stick your hand out there. Now it's going much, much faster. Same air, same wind or lack of wind that there was before, but now you're going so much faster. Now the speed of the object increases the air resistance. So the faster you go, the more air resistance there is. All right, and as an object is falling, it speeds up 10 meters per second. All right, but as it speeds up, you also get more air resistance pushing back up against it, and at some point, you're going to reach a point where the air resistance gets high enough that it equals the force of gravity pulling it down, that accelerates it, the acceleration of gravity, I should say. And so eventually it's going to hit a point where, since they're equal, you have a net force of 0, and it begins to fall at a constant velocity. Okay, and so if you jump off a building, you don't just constantly speed up, speed up, speed up, speed up. Eventually, you're going to reach a speed and you can't go any faster. Now, it's very likely 50, 60 miles an hour, and at that speed, you're going to splat into the ground. Okay, and so what we do, theoretically, hopefully, if you're jumping out of an airplane or something like that, is that you have a parachute. Okay, and at some point, you're going to pop that parachute, which increases your air resistance, and therefore, with that air resistance, you have a constant velocity of hopefully a lot less, maybe 5 to 10 miles per hour. All right, and maybe 15. You could still hurt yourself if you don't land properly, but it's a lot less damage than if you were, in fact, going at 50 or 60. Okay, so for example, we have our friend here, Mr. G.I. Joe. All right, I don't know if you can see this up here. I'm going to put it up here. If I drop it, at first, he accelerates. In fact, most of the time that you could probably see on the camera, he accelerates. But this time I'm going to put it down at the bottom. Maybe you can see a little better when the parachute comes open. All right, try it again. Okay, now he slows down. Once the parachute deploys, he has a greater air resistance. Okay, and because of that greater air resistance, he hits a constant velocity at a lower temperature. Now, say we have two parachutists, all right, but this one, gonna be the one on my right. It has a weight tapped on it, so he's gained a lot of weight. Okay, he's heavier, weighs twice as much as this one or more. Okay. The question is, when I drop them, are they going to fall at the same rate? Well, we said all objects acted on by gravity accelerate at the same rate. But this one has more mass. So it's going to have a greater force of gravity acting on it. Okay, so they're going to fall at the same rate to begin with until they reach their terminal velocity. This one hits terminal velocity and it slows down, doesn't speed up anymore. This one keeps speeding up. Why? Because it has a greater force of gravity. It needs a bigger force of air resistance before it hits that terminal velocity. So it will go faster and it will have a higher terminal velocity than this one. Okay, but they will go the same speed till this one hits terminal velocity, then it will hit a constant speed, and this one will keep speeding up until it hits a constant velocity. Then they'll have a constant velocity until they hit the ground, but this one's going to hit the ground much sooner because it's at a higher terminal velocity. All right, and so if you put a heavy person in a small person's parachute, they may very well hit at a higher velocity. So they have bigger parachutes for different weight classes. Okay, now I'm going to try to do this again. I'll tell you what, let's just scoot over here. And we'll drop these two and see if, in fact, that's how it works out. All right, let's start this. Pull them up to the ceiling as far as I can. All right. And 1, 2, 3, go. And basically, I think that's what you saw. Okay, the pink parachute, going with the weight, did hit the ground first. Okay, why? Because it took longer for it to reach a terminal velocity, and that terminal velocity was higher than the lighter one, and so it hits sooner. Okay, all right. Now, obviously, there wasn't much height here, so it would be magnified if you were actually jumping out of an airplane, which, frankly, I can think of no good reason for jumping out of an airplane. Okay, perfectly good airplane, you should stay in it. That's just my theory. All right, but basically, that's basically it. Okay, free fall is when only gravity's working on you. In real life, that doesn't really happen very often on Earth, anyhow. Out in space, things like that, yes. But here on Earth, for the most part, we always have air resistance reserved on us, and eventually that will result in a terminal velocity. If I remember, I'll post the video. They did a Mythbusters about dropping a penny off the Empire State Building. Well, the thing is, eventually it will hit a terminal velocity. It won't just keep going faster and faster. If it could keep going faster and faster, then yes, it would do some serious damage. It might be like a bullet by the time it hits somebody. But it reaches the terminal velocity. Would it feel good if it hit you? Probably not. If it hit you in the eye, soft tissue, yeah, it could be bad. But for the most part, it would just leave a little bruise or something probably, and that would be okay. Why? Because it would hit a terminal velocity before it didn't weigh that much. So it wouldn't have a big force of gravity. It hit a terminal velocity that would keep it from being harmful to people. All right, that's it for this week. Have a good week. Enjoy the quiz. And, on the quiz this week, I will try to put the blocker on it, lockdown browser. And so you'll need to install that before you take the quiz. And I'm going to do it now before we have a test so that we can work out any bugs in the system and get it to work properly before then. All right? Okay, otherwise, make sure you do that. Another thing, if you're turning in questions, make sure that you put your answers either in bold print or a different color or a space so that they stand out and make it easier for me to grade. I certainly appreciate that. A lot of people are doing that, but some people have not done that yet. So please make sure that you either bold your answers or indent and space so that they stand out from your questions, and that makes it a lot easier on these old people to grade, which would be me. All right, so have a great week. Talk to you later. Bye.